Hello everyone, and welcome to my video on Taylor polynomial and series. And so at this point, we've seen how to construct the Maclaurin polynomial and Maclaurin series. And the thing about both of those, the polynomial and series, Maclaurin polynomial series, is that they are solely centered at zero, at x equals to zero. And so this means that they are anchored to the particular function at x equals to zero. Now, just going to do a little algebraic review. If we say have the function f of x is equal to x squared, we're familiar with that particular function, and that's just a quadratic function whose graph is a parabola. If we were to say, I'm going to want to do a slightly different function, notation. If we were to say make the function g of x equals to x minus 3 squared, we know that from your work in Algebra 2 that to go from the function f to the function g, because we're subtracting 3 directly from x, this is going to cause a translation of the original parabola to go 3 units to the right. Right, so this we shift right by 3. And then in a similar fashion, if we have another function h of x, which is equal to, let's say, x plus 5 squared, well, from the original function f to this function h, right, we're going to cause another horizontal translation, but now in particular, we're going to shift now to the left by 5. And so the thing is, we have here this easy way to translate horizontally any particular function, and specifically polynomial functions. And I claim that's what we're going to do to, in particular, develop the Taylor polynomial and the Taylor series. What we essentially can do to perhaps anchor the Taylor polynomial and or series, anchor it to any x value on the original function, not just solely at x equals to 0, which is your Maclaurin polynomial and series. But if we just want to anchor the polynomial and also thus the series, perhaps, to any x value on your function, essentially we can just do the same thing that we do here, where to shift things horizontally to the left to the right, we can just add or subtract a particular value to each x value in the polynomial, and we get that horizontal shift. And so the basic way to construct the nth degree Taylor polynomial to a function y equals f of x centered at x equals to a, well, it's the same essential formula that we see with our Maclaurin polynomial, except we will subtract from each x value in the polynomial a. So we see here this x to the first power, we're subtracting a from that. This x being squared, well, we're going to subtract a from that, and so on. For every power of x, we just subtract a. And then the other adjustment we have to make to ensure that the Taylor polynomial behaves exactly like our function at x equals to a is that instead of evaluating the function and its derivatives at 0, like we did for the Maclaurin polynomial, we evaluate the function and each derivative of f at x equals to a to ensure that the polynomial behaves exactly like our function at x equals to a. And so this is the nth degree Taylor polynomial to the function y equals to f of x at x equals to a. And this is really the formula that you'll want to have memorized for your test. Because even if you want to find the Maclaurin polynomial, I claim that this formula will still work for that. Because the Maclaurin polynomial, we just center at x equals to 0. And this formula will turn into that Maclaurin polynomial formula that I already showed you in my prior videos, Just by plugging in 0 for a, you get that formula. So with that being said, let's now take a look at utilizing this Maclaurin polynomial formula to answer certain questions. So here we have an example. We want to find the third degree Taylor polynomial to f of x equals to ln of x centered at x equals to 2. And to do this, you would repeat and perform the same steps that I told you to perform when constructing the Maclaurin polynomial. And so thus I'm going to first evaluate the function f and its derivatives up to the third derivative because we're finding a third degree Taylor polynomial. And we'll evaluate each of them at x equals to 2. So starting off with f of 2 would simply just be natural log of 2. Then the first derivative of our function ln of x would be 1 over x. And because we're going to have to derive this a couple more times, I'm just going to rewrite that as x to the negative first power. For the sake of putting together our polynomial formula, we can evaluate this first derivative at 2, and we would get that's equal to just 1/2. The second derivative of our function would be negative x to the negative 2. And then evaluating that second derivative at 2, we would get negative 2 to the negative 2. To make my life a little bit easier, I'm going to get rid of the negative exponent and write that as negative 1 over 2 squared, which is the same thing as negative 1/4. And then, because we're writing a third degree Taylor polynomial, we got to get up to the x to the third term. And so we got to get to the third derivative here in our analysis. So the third derivative would be 2x to the negative 3. If we evaluate that at 2, we would get 2 times 2 to the negative 3. And just to make my life a little bit easier, if we get rid of the negative exponent, we would have 2 over 2 cubed, and 2 cubed is just 8. So now we have our function and its derivatives up to the third derivative evaluated at 2. And now we can put together our Taylor polynomial formula, our third degree Taylor polynomial formula. So I'll just write p of sub 3 of x, and using our formula, we start off with f of 2 first, that's just ln of 2. And then the next term would be our x to the first term. But because it's the Taylor polynomial centered at 2, we're going to want to subtract 2 from that x to the first term. So we have x minus 2 to the first. And in front of this should go f prime of 2, which we calculate as 1/2. The next term after that would be our x squared term. But again, we're centering at x equals 2. So we're going to write x minus 2, that whole thing squared. In front of that power of x, we should see in the denominator 2 factorial, and in the numerator we should see f double prime of 2, which we have here as negative 1/4. And then I'm just going to write the last term down below here. The last term, it's going to be our x to the third power, but we're going to once again subtract by 2 from x first before we cube that. And in front of that term, we should see a coefficient that has 3 factorial in the denominator, and in the numerator should go the f triple prime term evaluated at 2, and that we simplified or got as the value of 2 over 8. And so here this would be our third degree Taylor polynomial to the function natural log of x centered at x equals to 2. All right. So we'll just do one more problem, just practicing utilizing our Taylor polynomial formula, which we can also technically use to help find the first several terms to a Taylor series. So this example here asks to find the first 3 non-zero terms to the Taylor series of f of x equals e to the 2x centered at x equals to 1. Now, because we're centering the series at x equals to 1, we can't use those shortcuts that you learned about with our Maclaurin series. the e to the x Maclaurin series cannot be specifically used here to find this first three non-zero terms. You don't want to go down that route. So we're just going to have to find and evaluate this function and its first two derivatives to get the first three non-zero terms to this Taylor series. So starting off with f of 1, f of 1 would just be simply e to the 2 times 1, or just e squared. The second term we would get by, that would be the x of the first term, so we can derive our function e to the 2x. Be careful, we'd have to do chain rule there. We would get 2 times e to the 2x, and evaluate at 1, that would be 2e squared. And then the third term would be what we get when we get the x squared term. So the second derivative of our function here would be 4e to the 2x, and evaluated at 1, that would be 4e squared. So now, having these first three values of our function and first two derivatives here, they're all not zero. We can use these to get the first three non-zero terms to this Taylor series for e to the 2x. And so now e to the 2x, the Taylor series centered at 1, it would just be f of 1 first, just that constant. The next term would be the x to the first term, and because we're centering at 1, we would write x minus 1 to the first power, and in front of that would go just f prime of 1, which was 2e squared. And then the next term in our Taylor series here would be the x squared term, but we have to subtract 1 from that first, so we had x minus 1 squared. The coefficient to that x minus 1 squared, the denominator would be 2 factorial, and the numerator would be the f double prime value at x equals to 1 to our function, which was 4e squared. And as a series, this would continue going on and on forever, but at least this here gives us the first three non-zero terms to this Taylor series of our function centered at x equals to 1. I hope this video helps you with understanding Taylor series, and I hope you have a wonderful rest of the day. Take care, everyone.